Hello, this is a simulation problem from the PhET program that we worked with in class on the moving man. This problem states that a moving man starts at a position of negative 8 meters and moves with an initial velocity of 12 meters per second with a constant acceleration of negative 4 meters per second squared. Draw the three graphs. So we're being asked to draw a position, a velocity, and an acceleration graph for the situation described above. We're supposed to draw these three graphs and log into PhET and to observe and see how our prediction compares to what PhET actually shows. To begin this problem, I often like to start with a velocity graph. The velocity graph is often the most useful graph with these types of problems. And here it states that it starts off with an initial velocity of 12 meters per second. And the acceleration is negative 4 meters per second squared. As we talked about, this acceleration basically means that the velocity changes at a rate of negative 4 meters per second every second. So after 1 second, the velocity would then be 8 meters per second. Another second goes by, the velocity would be 4. Another second goes by, the velocity is now 0. And one more second, the velocity then would be a negative 4 meters per second, which basically means that the man is moving in the opposite direction. So if we graph this data right here, this is basically our velocity versus time graph right here. And this is linear, as you can see. So over here in the velocity graph, we start with a velocity of 12 meters per second, and then after 3 seconds we're at rest. The graph basically looks like this here, and our velocity versus time graph is done. We also know that the slope of the velocity graph gives us the acceleration graph. And if we look at the slope of this graph is a rise over the run, which is the rise is the change in velocity. The run is a change in time. If we look at this part of the graph right here, we can see the velocity changes by negative 12 meters per second over a time period of 3 seconds, which gives us a slope of negative 4 meters per second, which basically is our acceleration, which matches with what we were given. This acceleration is constant. It never changes. So on the acceleration graph, if we at negative 4 meters per second, or negative 4 meters per second squared, the acceleration is constant. It does not change. So let's match this up right here. There we go. Acceleration graph is done. So with these constant acceleration graphs, the velocity will always be linear, and the acceleration graph will always be constant, as shown here. All right, now going to the position graph. Position graph says it starts at negative 8 meters. Negative 8 meters. So negative 8 meters, we'll make that negative 8 meters right there. And we know that the slope of the position graph will tell us the velocity. And so we look at this, the velocity graph is at positive 12 meters per second, which basically says the slope of this graph is a positive, it's going to be positive 12. So right here at the very beginning, the slope right here will be a positive 12. So we'll make it kind of look like that. And looking at this graph right here, we know that the velocity is 0, which means the slope of the position graph at 3 seconds, there's 3 seconds right here, will basically be 0. It'll be flat. And then as we go along, you can see the velocity becomes negative, which means the slope is negative. So here towards the end, or after 3 seconds, the slope becomes negative. So we can kind of see the pattern taking place here. And the position graph kind of looks like this. It's a parabolic relationship right there. And we get that for the shape. if we want to be more precise, we know that the area of the velocity graph tells us our displacement. So from 0 to 3 seconds, this area, which in this case is a triangle, will tell us the displacement from 0 to 3 seconds. So the area of a triangle, the area is the displacement. In this case, it's a triangle, so 1/2 the base, which is 3 seconds, times the height, which is 12 meters per second. You see seconds cancel out right there. Gives a displacement of positive 18 meters. So over the time period of 3 seconds, if we start at negative 8 meters and our displacement is 18 meters, our displacement of 18 meters would put us, let's see, negative 8, and we go in the positive x direction 18 meters. We'll put us right here at, that would be 10 meters right there. 10 meters. So this is not to scale, but we see the idea. We get the idea of what's going on here. All right, what else can we learn from these graphs? Let's see. The slope of the position graph gives us the velocity. So the slope right here is 12. The slope right here is 0. Velocity is 0. The slope here is negative. Velocity is negative. We know the slope of the acceleration, slope of the velocity graph gives us the acceleration. We see the slope is constant and also negative. You see our acceleration is constant and also negative. And then working backwards, we know that the area of the acceleration graph gives us the change in velocity. So for example, let's say in the first 3 seconds right here, if we take this area right here, this area, we know the area, in this case it's a rectangle, is a change of velocity. The change of velocity is the area, which is length times width. So we'll say 3 seconds times negative 4 meters per second right there. You see seconds cancel out right there. So this gives us negative 12 meters per second. Negative 12 meters per second. So from time t equals 0 to time t equals 3, the velocity changed by negative 12. If we look up here with our velocity graph, in the first 3 seconds, our velocity changed by negative 12. Everything matches up. So interesting, slope of this graph gives us this graph, the slope of this graph gives us this graph, the area of this graph gives us this, and the area of this gives us that right there. There is one last question here. It says, determine the time at which the man turns around. Determine how far the man traveled before he turned around. Well, we can see that in the position graph, he's traveling in the positive x direction. At this point, at 10 meters, he then travels in the negative x direction. So you can see at this point he turns around. We can also see the velocity graph that in this region right here from 0 to 3 seconds, his velocity is positive, which means he's going in the positive x direction. And after 3 seconds, his velocity is negative, which shows an opposite direction. So at 3 seconds, he turns around, and we've already figured out that in that time right there, he turns around at a position of 10 meters, or also you can say he basically traveled in the positive x direction 18 meters before he turned around. All right, hope this helps out. All right, thank you.